What would be our strategy for a tangent secant trig integral? That's what we want to look at here for a few minutes. Well, turns out it depends again. Like sines and cosines, depends on odd and even power. Well, sort of the same thing happens with tangent and secant. a little different, but we'll talk about it. And of course, the identity we use is the other Pythagorean identity, or comes out of the Pythagorean identity with tangents and secants. That is the secant squared. The identity we're going to use is secant squared x equals tangent squared x plus 1. Or the other possibility there is if we want to replace, so that's if I want to replace secant squared. If I want to replace tangent squared there, notice, we'll subtract the 1 over, right? Tangent squared is secant squared x minus 1. Secant squared x is tangent squared x minus 1. Tangent squared is secant squared x minus 1. All right, so here's the ones that we can do with the process that we're talking about. If, let's call this strategies for this. The A one, the first one, if tan is odd, so we've got an odd powered tan, so if m here is an odd number, save out a factor of tangent x secant x, and so that's kind of gets it complicated. So I'm going to pull a tangent and a secant out with my and save it. So that just means put it over there with the dx, and then express the tans express the remaining tangent x's using the trig identity tangent squared equals secant squared x minus 1. So then express the tangent x's in using the trig identity tangent squared equals secant squared minus 1. Well, the other possibility then, if tangent is not odd and secant is even, so the other possibility that we have, if secant is even, then this sort of integral is going to work out pretty nicely, because what we're going to do then is save secant squared x out. In other words, put it out here with the dx, save a secant squared x out, and then express the remaining, then express the secant x's that are remaining in a different form using the secant squared x equals tangent squared x minus plus 1. All right, so may not make a whole lot of sense there, but here's what I mean by that. Tangent to the 6th times secant to the 4th x dx. Let's look at that interval. Okay, so let's examine, see what we got. We've got even and odd power, both the secant and the tangent are even. Well, tangent is odd, so that A strategy, that is not going to apply here. yeah, we're going to utilize the second one. Secant is even, so I'm going to save out a secant squared x, so that means I'm going to have tangent to the 6th x times secant squared x times the secant squared x. So just divvy up the secant to the 4th into 2, but specifically I want a secant squared x dx. All right, so we did that. So then express the secant of x's out, the remaining ones there, in terms of tangent squared x plus 1. So I'm going to take this secant squared and rewrite it as tangent squared x plus 1. Okay? Well, reason this works out nicely is because now if I distribute that tangent to the 6th, what I'm going to get is tangent to the 8th. So distribute this tangent to the 6th. So that would be tangent to the 8th x plus tangent to the 6th x times secant squared x dx. And the reason this works is because now a little u substitution will go a long way here, because if I let u be tangent of x, look how this works out so very nicely. The du, well, the du is the derivative of tangent, which is secant squared, so that's why we saved out that secant squared x before. And you can look at it, that's du. Divide by secant squared, so the secant squared is going to cancel however we think of it. Here's what we got. Don't we have then u to the 8th plus u to the 6th, and the secant squared x is going to cancel out because du is du over, dx is du over secant squared x. Yeah, those are going to go out. So we just have u to the 8th plus u to the 6th du. That is just a power rule antiderivative, 1/9 u to the 9th plus 1/7 u to the 7th plus c. So it's 1/9, the u was tangent, so it'll be 1/9 tangent to the 9th x plus 1/7 tangent to the 7th x plus c. Okay? Okay? Well, let's try one more here. I'll leave those strategies up there so we can reference them. All right, so it also works well on this one. Tangent to the 5th theta times secant to the 7th theta d theta. Okay. Well, in this case, we've got the A strategy is going to kick in here because we've got an odd tangent. And so we can use strategy A here. Tangent is odd, so we're going to save out a tangent x, secant x. So I'm actually going to pull out a tangent theta and a secant theta over here with my d theta. So that'll bring it down to tangent to the 4th theta, secant to the 6th theta, and then I'm going to write the tangent theta, secant theta. Got those other two pieces over there. So I pulled out a tangent and I pulled out a secant. So both of those decrease by 1. All right, then express these tangents that are left over here in terms of secant tangent squared x equals secant squared x minus 1. Well, this is tangent to the 4th, so I've got to do my tangent squared theta squared thing. All right, so I can do that replacement. Change that to tangent squared squared. And 4 it out, or replace it and then full it out. So tangent squared theta by this identity is secant squared theta minus 1. So I have secant squared theta minus 1 squared. And so again, I've seen this a couple of times in previous examples. I got to multiply that out. Secant squared theta minus 1 times secant squared theta minus 1. So secant squared, secant to the fourth theta minus secant squared theta, then you got a minus secant squared theta, so you got minus 2 secant squared theta. And then you have minus 1 times a minus 1, you have a plus 1. Okay. Almost there. Just distribute now secant to the 6th theta. So the integral of secant to the 10th theta minus 2 times secant to the 8th theta, and then of course plus secant to the 6th of theta times the tangent theta. Secant theta d theta. Well, all this pays off because now use substitution. U equals secant theta, and so then du, well, the derivative of secant theta is secant theta tangent theta d theta. And so if I divide by secant theta tangent theta, that's my replacement for d theta. And notice it's going to go really nicely there. Cancel those out. Yeah, so if you have those, they work out pretty nicely. So we've got integral, so u to the 10th, replace the secant theta by u, so it'll be u to the 10th minus 2u to the 8th, plus u to the 6th. And then, as you can see, those secant theta, tangent thetas, are going to cancel because of yeah. So now we just have power. 1/11th u to the 11th minus 2/9 u to the 9th plus 1/7 u to the 7th plus c, and then change those back. The u was secant, so it'd be 1/11th secant to the 11th x theta minus 2/9 secant to the 9th theta plus 1/7 secant to the 7th